This is implicit in class examples. And there's not a whole lot of implicit questions that I've seen on past AP tests, but they do exist. There have been some, so we're going to cover it. Consider the curve given by x squared plus 4y squared equals 7 plus 3xy. Show that the derivative is this. Well, we're going to take the derivative implicitly. So there's 2x, 8y dy dx. The derivative of that will be 0. And then we have first times derivative of the second, and that's down here. First times derivative of the second. Now the derivative of the second is 1, but it's the derivative of y, so we need dy dx. Plus the second times the derivative of the first, and then we get 3y at the end there. Now we've subtracted over the 3y dy dx, factored out the dy dx, and subtract the 2x. And then all we have to do is divide by 8y minus 3x, and we got it. Letter B, show that there is a point P with x-coordinate 3, at which the line tangent to the curve at P is horizontal. Find the y-coordinate of P. We're going to we're going to set the top of the derivative equal to 0, because that's how you make the derivative 0. That's how you make the tangent line horizontal. We have a derivative of 0. We get 3y minus 2x equals 0. We know that x is 3, so we're going to plug 3 in here. Add over 6, divide by 3, and we know that y is 2. So here's the point we're looking at. Now we just have to show that that point is actually on the curve. So we plug 3 in for x, plug 2 in for y, and we see that we end up getting 25 equals 25. Letter C, find the value of dy, or second derivative, at the point P found in part B. Does the curve have a local maximum, a local minimum, or neither at the point P? And justify your answer. Well, we need the second derivative, so we have bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. But notice that when we evaluate the first derivative at 3, 2, we get 6 minus 6. That is 0. So the slope is 0. So that's why we see a couple zeros over here. Well, when, when we get done evaluating at the point 3, 2, we get a negative for the second derivative, which means the curve is concave down, so we have a local maximum there. Since the first derivative is 0 and the second derivative is negative, local max at 3, 2. And here is the rubric. If x natural log x squared, if y equals that, then the first derivative is first times derivative of second plus second times derivative of the first, and derivative of first is 1. The x's cancel out here, and then we can factor out a natural log of x, and we get letter C. If, let's see, I have, give me a second here. Let me get rid of this. And I'll probably write this back in, but I was taking a look at this earlier. And I wanted to go back and erase this. Not that it's a big deal, but here we go. If the integral from 0 to 6 of that function is approximated by 3 inscribed rectangles of equal width on the x-axis, then the approximation is, I graphed this parabola roughly, very roughly, by plugging in 0, 2, and 4. And looks like I plugged in 6 also, just to complete it, because we're going from 0 to 6. But if we're going to inscribe the rectangles, then this one needs to be below from 0 to 2. And notice this 3 of equal width. And then in order to get this one to be inscribed, it'd have to be a left, kind of a left Riemann sum, even though the total thing isn't left Riemann sum, because on this one we're actually doing midpoint. So it's kind of a hybrid between them, but that's how you're going to inscribe the rectangles. Well, this is a 2 by 1. This is a 2 by 2. This is a 2 by 10. So I just factored out the 2 here. 1 plus 2 plus 10, 13. We end up with 26. A particle moves on the x-axis at any time t. Its velocity is subject to the condition x of 0 equals 0. There's an initial value, where x of t is the position function. Which of the following is an expression for x of t? Well, we know that kind of saying the velocity, well, v of t, is, we'll say it's the derivative, which is sine of 2t. We'll integrate both sides, and we get x is equal to, 1/2 cosine of 2t and then plus c. And here's where we use the initial condition. And we find out that c is 1/2. So here is the function for x of t, letter D. Which of the following is the equation for dy dx whose slope field is shown below for -3 to 3 and -10y to the 10? So we're saying that the slopes are following the values of y. Well, that's not true because I don't see here where y is 1 that we have a slope of 1. Letter B says the slopes are following an exponential function, e to the x. Don't see that at all. C, sine of x. So the slopes are following sine of x. Well, the slope at 0 of sine of x is 1 because it would do something like that. And it certainly doesn't go up to, and I know it's hard to tell, but this is like almost going straight up over here. So it's not sine of x. I don't see these slopes following any kind of parabola, so it has to be letter E. Now, the function looks like something like this, which is the shape of an x to the 4th, and if you take the derivative of an x to the 4th, you get an x to the 3rd. The Taylor series for sine of x squared over x squared centered at 0, a Maclaurin, is, well, sine of x is an odd function. Or excuse me, odd function. So here we get the odd powers, and of course, sine is an alternating sequence. Then we're going to replace x with x squared, so x squared, 6th, 10th, 14th. But then we're going to factor out or divide out 2 of those x's. So then that becomes 1, x to the 4th, x to the 8th, x to the 12th. Now notice that it going 1, 4, 8, 12 is increasing by 4. That's linear. So there's why we have x to the 4k if we start at 0. -1 to the k because we want -1 to the 0. We want +1. And then in the bottom, this is odd powers with 1 factorial, 3 factorial, 5 factorial, and so on. Well, 2 times k would get you an odd number. If we're going to start at 0, we get 0, and then we just have to add 1 to that. So it ends up being letter E. If the length of a curve y equals f of x from a to b is given by the length of a curve. Well, the length of a curve is the square root, there is square root in it, integral from a to b of the square root of 1 plus the derivative squared. So somehow we have to find the derivative squared in this in order to find the actual function. We can borrow 1 from 2, so we get 1 plus 1. This factors into e to the x plus 1 times e to the x plus 1, e to the x plus 1 squared, and we know that that's the derivative squared. So now we know the derivative is e to the x plus 1. Well, if we integrate e to the x plus 1, we get e to the x plus x, and then plus some constant. So what we're really looking for is, do they have e to the x plus x? Now, if they have 2 different constants, we wouldn't be able to answer this problem. But the only answer that has e to the x plus x is letter E. And then it wouldn't even matter what the constant is because we would take the derivative of that and then we would find the length from there. The maximum value on -1 to 2 is, this one, we have endpoints. So to find any kind of min or max in between those endpoints, we take the derivative, set it equal to 0, and solve. Turns out 2 and 1 are candidates, but we know what these look like that, because it's a positive x to the 3rd. So we're looking for a maximum. So the first one's a maximum, and the second one is a local minimum. So we only have to really try x equals 1, especially if it's a multiple choice problem. But here's one endpoint, -1. Here's the other one. So we got -24. 3 is the winner right now, but then when you plug in f of 1, 4 ends up being the winner. So 4 is the actual maximum value. Let R of t represent the rate at which water is leaking out of a tank where t is measured in hours. Which of the following expression represents the total amount of water that leaks out of the first 3 hours? Well, if R of t is the rate, then we're going to have to integrate. We're going to have to go backwards to get the amount. So the only one that really goes backwards that integrates R of t would be 0 to 3. This would be the average value of the rate. What would this be? This would be the average rate of change of the rate. So that would be well, I'm gonna try average acceleration, I suppose you could say. This one certainly ends up being this would just be the difference in rate, I guess. I don't know.